Alrighty, hello and good morning, everybody, and welcome to the live OpenSSL webinar, Writing a TLS Client with our very own OpenSSL engineer, Matt Caswell. My name is Cosmo Subcoda, and I will be moderating this webinar. As a reminder, all attendees will be in listen-only mode. If you have any questions, please feel free to use the Q&A box or raise your hand if you'd like to ask the question live, as we will be hosting a Q&A session following this presentation. This webinar is also being recorded and will be made available on our YouTube channel following the presentation. Our YouTube channel is just at OpenSSL_. I also invite everyone to follow us on Twitter, as well as subscribe to us on YouTube. We're just at OpenSSL_ on all of our social media. And if you have any questions or comments, please feel free to email us at feedback, that's FEEDBACK @openssl.org. And this webinar will be recorded and emailed to you after the presentation, as well as you can find the slide deck in the follow-up email as well. And now I hand everything off to Matt for the rest of the presentation.
Thanks, Kajal. Welcome everyone. Thanks for coming. Writing a TLS client. Let me just summarize what we're going to do today. I'm going to spend a little bit of time just talking about TLS itself and talk about some basic TLS concepts. I'm going to briefly introduce certificates and trusted certificate stores. I'm going to talk about some of the important OpenSSL objects that you'll need to use in order to write an application. And then the main event really is to write a simple blocking TLS client. And it will just connect to a server and exchange some application data with it. I am making some assumptions. So most importantly, I am going to be showing C code. So I'm assuming that you're familiar enough with C to be able to read that. We start from a position where we assume that the OpenSSL library has already been installed, and you can refer to some of our other videos about that if that's not the case. And I'm also going to assume that you have a trusted certificate store set up. And again, I'll talk a little bit about that later on. Okay. So let's start. So first of all, what is TLS? So it stands for for Transport Layer Security, and it's just a protocol that enables communication between applications on a network, and it provides three main services. So first of all, confidentiality. So you can be sure that if you're using TLS, the data that you exchange with your other party is confidential. Any eavesdropper won't be able to view the plain text. It provides integrity. So if there was some malicious person who was some man-in-the-middle attacker, for example, who was able to change the data that's being exchanged, then you would know about that through the protocol. The protocol would fail and say, no, the integrity has failed. And finally, it provides authentication. So as a client, you will be able to authenticate the server that you're talking to and know that the server is what it claims to be. The protocol itself is built up on top of lower underlying protocols, so TCP/IP in this case. So the TCP/IP layer just provides the transport capability, so the capability to shift bytes from one endpoint to the other endpoint, and the TLS adds the security layer on top of that. Sometimes you will hear it referred to by the name of its predecessor, which is SSL, but these days we just call it TLS. There are various different versions of the protocol available. Most commonly today, you will encounter TLS 1.3 and TLS 1.2. Really, you should be avoiding anything less than TLS 1.2 if at all possible. Okay, so in order to write our TLS client application, we're going to have to use some objects that the OpenSSL library provides to us. The most important one of those is the SSL object, and the SSL object represents a TLS connection in an application. In order to create one of those, we use another object, which we call the SSL underscore CTX, or just SSL context object. So you can think of an SSL context as a bit like a factory. Its job is to create other SSL objects, or create SSL objects. So normally you would create one SSL context. You do that probably early in your application, maybe in your main function of your application. So you create one of those, and then for every TLS connection that you want to create, then you will create an SSL object. You can apply configuration options to your SSL context, and then all of the SSL objects that you create from it will inherit all of those configuration options. Okay, we also, for each SSL object that we create, we have to associate two BIO objects to it. So a BIO is just an abstraction for some kind of input-output concept. So, for example, typically like a socket, if you're talking in TCP/IP terms. And there's two, one for reading and one for writing. But in most cases, you're going to use the same BIO for both. So yeah, so the BIO, in this case is representing that underlying transport layer, that TCP/IP socket. So let's dive into some code. So the first thing we need to do is create an SSL context. And we have a function for that, SSL underscore CTX underscore new, which creates one of those. It takes one argument, which tells us what kind of SSL context we want. Do we want one for a client, or do we want one for a server? Do we want is it for TLS or some other protocol? Well, there are a few options available for us here, but for the purposes of this webinar, we're talking a TLS client. So so here's the code at the bottom of the screen there. SSL context new with the we pass in the TLS client method, and it returns our SSL CTX object. We do have to make sure that we check for errors. Errors can occur. So, for example, we can fail to allocate the memory. And an error is just indicated by a null return from that function. So in the event of an error, in this example, we're just bailing out. Okay, so once we have our SSL CTX object, we can now apply any configuration that we want to apply that's going to be common to all of the TLS connections, all of the SSL objects that we create from this SSL context. So in this example, we're going to set the minimum protocol version that we're going to accept as TLS version 1.2. We don't want anything below that. So we just call this function SSL CTX set min proto version. We pass in our SSL context object that we created on the previous slide, and we pass in the TLS 1.2 version that is the minimum. Again, this can fail. it will return a 0 value as a result if it fails, and in that eventuality we'll just bail out again. Okay, so I just want to take a brief detour and talk about certificates for a bit. So our TLS client needs to authenticate the server that it's going to talk to. So which means it needs to confirm that the server is what it claims to be and not some imposter. So, for example, if you're going to connect to openssl.org, you want to know that you're actually talking to a server operated by openssl.org and not some, you know, some attacker who's just pretending to be us. So for this to work, the server sends the client a certificate, which you'll often hear referred to as an X509 certificate. And the certificate contains various information, including a public key. So it's not the public key itself, it contains the public key. And it's got other information, such as the domain name of the server. The server itself holds the private key. That's kept secret, and it's the private key that corresponds to the public key in the certificate. And as part of the protocol, the server will prove to the client that it actually holds that private key. And it does that by signing a message with the private key and sending it to the client. And then the client checks the signature. It uses the public key that it's obtained from the certificate and can then authenticate that, yeah, the server is what it claims to be. So we also have this concept of certification authorities, or CAs. So the certificate itself is signed as well. So that's not to be confused with any signature that the server creates. There is a signature in the certificate itself, which was created by the CA. And the public key that the CA owns is also stored in a separate certificate, the CA certificate. So that CA is a third-party organization, and its responsibility is to verify the information presented in the server's certificate, including things like the DNS hostname. So the CA will only sign the server certificate if it's been able to validate that the server really does have control over that DNS hostname. These CA certificates can be chained together into a trust chain. But the client only actually needs to trust the root CA in that chain. The server sends its certificate and any intermediate CA certificates to the client, and then this client is able to verify the whole chain back to a CA that it knows that it trusts. So all of that only works if that chain of trust can be built between the certificate that the server sends you, any intermediate certificates, CA certificates that it also sends, and the root CA that the client already knows that it trusts. And for that to work, the client must have a set of those CAs that it knows it trusts. So it's just important to point out that the OpenSSL source code itself doesn't come with a trusted certificate store. It doesn't come with a set of these trusted CAs. You would normally get this store from your operating system. So if you're on a Linux distribution, then they normally come with a trusted certificate store. Otherwise, there are other third parties that you can get them from. I'm assuming within this presentation that you've already got one. There is some more information on this and some tips on where you might be able to get hold of this at the link on the screen. So in our TLS client application, we need to configure that client to do the verification and abort the handshake if the verification fails. It's an important part of the TLS protocol that we don't want to talk to a server unless we can verify it is what it says it is. So to do that, we call this function SSL CTX set verify. We pass in the SSL context object that we created earlier. We pass in this argument SSL verify peer, which just says to OpenSSL, verify the certificate and abort the handshake if the verification fails. And we just pass null for the third argument. We're not interested in that for the purposes of this presentation. We also need to configure the SSL context with the trusted certificate store and tell it where it can find that store. And in most cases, you just want to tell it to use the default store location. And you can do that with this function SSL CTX set default verify paths. So there's the code at the bottom of the screen there. You just call that. Again, it can fail. And if it does, then again, we're just going to bail out. Okay, so now we have our SSL context. It's set up, it's configured. It knows where its trusted certificate store is. Now we need to create the TLS connection itself. The client always initiates this, and it creates it using the SSL CTX that we created earlier. We can, if we want, apply some connection-specific configuration to that SSL object. We also need to create some BIO objects to represent the underlying TCP socket for our connection, and then associate that BIO with the SSL. Once we've done all that, then we can initiate what we call the TLS handshake, which is a process by which the client and server exchange TLS protocol handshake messages. And the end point of that is that we have our TLS connection set up. And from that point on, we can then just exchange, we can read and write arbitrary application data to the connection and exchange that with our server. So to create the SSL object, we call this function SSL underscore new, and it just takes one argument, which is the SSL CTX that we created earlier. There's the code at the bottom of the screen. Obviously, if this is the second or third SSL object that we're creating, we don't need to go through all of that SSL context creation step again. We can just skip straight to this point. We've already got our SSL context. We can just go straight to this point. We do need to check for errors. So again, an error is indicated by a null return from this function. And if that occurs, again, in this presentation, we're just bailing out. Okay, so now we need to create our socket. You can use platform-specific APIs for this to create your socket. So whatever platform you're on, just use the normal functions for that platform to create those. Or alternatively, OpenSSL does have some portable functions that wrap those platform-specific APIs, so you can use those instead if you prefer, and that's what we're going to do in this presentation. So what we're going to do is look up as the first step is look up the IP address of the host name we want to connect to, which for the purposes of this presentation is www.example.com. So we're going to look up the IP address, and then we're going to create a socket for that, and then connect that socket to the server. So this is just about creating the underlying TCP/IP connection. It's important to note that what I'm doing here is I'm going to be creating a blocking socket. So this means that for a blocking socket, if you read data from that socket, if there's no data available yet, then that function call to read will block. It will just wait until data is available, and it will only return either once the data is available or if some error has occurred. You can use non-blocking sockets if you want to. So with a non-blocking socket, if you attempt to read and there is no data, it will just return immediately, and you can go and do something else and come back later to check if data is available later. But for the purposes of simplicity, I'm just using blocking sockets in this presentation. Okay, so here's the code to create a socket. I'm using the OpenSSL portable APIs for this. So let's just look at that code. So one of the first steps there is we call this function bio lookup x, which looks up the IP address of the host that we're interested in, which is www.example.com. We're going to connect on port 443. So let's look up what the IP address is. We could actually get multiple IP addresses come back from that call. Sometimes multiple IP addresses are associated with the same host. And so we have a for loop here, which just loops through each of those IP addresses that we've got back in turn. And we're just going to keep going around that loop until we successfully connect to one of those IP addresses. So we create the socket. We call this function bio socket. We pass in the IP address information that we've obtained, and we try and create a socket. And then if that step is successful, then we connect it to the server. So we make this call bio connect. We pass in the socket and check again if that's been successful or not. If any of those things fail, then we go around the loop and try the next IP address until eventually, hopefully, we find an IP address that's working. We've created our socket. We've connected it to the server, and we can go on to the next step. So at this point, we have a working TCP/IP socket to the server. So now we need to associate that socket with a BIO object. This is an OpenSSL object, which is just an abstraction for doing I/O. You can get different types of BIOs. We're using a BIO S socket type, but there are other types. So we create our BIO. We call this function BIO new. We say we want a socket type by passing in bio S socket. Again, we check for errors. If that doesn't work, we'll get a null return. And again, we're just going to bail out if that happens. But assuming that it works, then we associate the socket file descriptor that we got from the previous slide with that bio by this function bio set fd. We pass in the bio object we just created. We pass in the socket file descriptor that we created on the previous slide, and we pass in this final argument, which is a flags argument basically. So in this case, we're passing bio close, which basically means that when we've finished with this bio, once we free the bio, it will automatically close the underlying socket for us, so we don't need to worry about that. You could optionally pass a different flag, bio no close, and if you do that, then it won't be closed automatically when we free the bio, so your application would have to do that explicitly. Okay, so we've got our SSL object, we've got our bio object, and now we associate the two together. And we do that by calling this function SSL set bio. And we pass in the SSL object is the first argument, and then we have two arguments, and we pass the same bio twice. And the reason for that is the SSL object can be associated with a different bio for reading that it uses for writing. In most cases, actually, you want it to be the same, and so and that's what we're doing here. And we just pass the same bio twice. Right. So the next thing we need to do is to tell OpenSSL the host name of the server that we're trying to connect to. And the reason we need to do that is so that we can verify that the certificate that the server presents is for the right server. So we do that through this function SSL underscore set1 underscore host. We pass in the SSL object and we tell it the host name of the server we're connecting to. Virtually all clients need to do this. Unless you're an expert user and really know what you're doing, you should be making this call. Okay. So that's the certificate verification host name. There is another host name. So some servers can actually host multiple host names from a single server instance, and each one could have a different certificate associated with it. So in order for the server to pick the right certificate, it needs to be told by the client what host name it's interested in. And this occurs through a process called server name indication, or just SNI for short. OpenSSL does all of that for you, but you do need to tell OpenSSL that host name, the SNI host name. In most cases, this is going to be exactly the same host name that we just set for certificate verification, but it doesn't have to be. There are some corner cases where this is different, and which is why we have to set it twice. But for most of the time, it's just going to be exactly the same that we've just previously set, and we do that through this function SSL set TLSX host underscore name. You pass in the SSL object, you pass in the host name, and again we must check for errors, and again we bail out if that fails. All right. So finally, we are now ready to try and create, actually connect to the server at the TLS level. So we perform the TLS handshake with the server, and we do that through a function SSL underscore connect. Remember I said we were using a blocking socket. So that means that this function, once you call it, it will only return once the handshake has finished, either successfully or with an error. But whilst the handshake is in progress, it basically will hang at this point until it's complete. It just takes the one argument, the SSL object that we created earlier. A return value which is less than 1 indicates a failure. And again, we're going to bail out if that occurs. Otherwise, if it's 1, then great. The handshake was successful. We've successfully created our TLS connection with the server. So I've got a bit more code in this example here of how to handle a failure. And I'm just showing you here that we can get a little bit more information. A common cause of failure at this point is because the certificate verification has failed. And that can be for a number of reasons. So if the SSL connect fails, I'm going to call this function SSL get verify result, and that gives us a code to tell us what happened when we tried to verify the certificate. And if the result is okay, then that tells us actually the verification was successful. It must have been something else that failed. Otherwise, we might want to know what the cause of that verification failure was, and we can call this function x509 verify cert error string, pass in the verify result code that we got, and that will give us back a human readable string which explains the cause of the verification failure. And in this example, I'm just printing it on the screen and then bailing out. Okay, so let's assume that our TLS connection was successful. We have established a connection with our server. We're now finally ready to exchange some data. We can send and receive data over this connection. In this example, we're just going to write a simple HTTP 1.0 request. And to do that, we're going to call a function SSL underscore write underscore X. Again, it's a blocking socket, so that function will only return once the write is successful. So we pass in the SSL object we're writing to. We're going to pass in the request data that we want to send, the length of that request data, and it gives us back the number of bytes that were written, which should be equal to the length of the request that we tried to send. Again, it could fail, and if it fails, you'll get a 0 return. And in this example, I'm just bailing out in that instance. Okay, so we've written our request. So HTTP 1.0, it's going to send us back a response. And we can read that data by calling SSL underscore read underscore X. Again, it's blocking socket, so it will only return. That function will wait until it's got data to return. And it will only come back once it's got data or some error has occurred. We don't actually know how much data we're expecting here. So we, in this example, I've put it in a loop, put it in a while loop. We're just going to keep looping until an error actually occurs. A valid error can be the server closing the connection, and that's actually normal in the case of HTTP 1.0. Once the server has finished sending its data, it just closes the connection. So we're just going to sit here in a loop reading that data. And in this case, I'm just writing it to the screen, writing it to standard out until we've got no more data. And then we break out of the loop. Something happened, some error occurred, which could just be the normal server closing the connection, or it could be some other error. But once that happens, we break out the loop and we've finished receiving application data. So now we just want to check, well, what was the reason for that error? And we can call this function SSL underscore get underscore error. We pass in the SSL object, and we also pass in the return code from the read call that we got, and we check what the error code is. And a normal graceful closure by the server will be indicated by a code of SSL error 0 return. So if we get that, then great, everything worked, no problems. If we get anything else, then that's some other kind of non-graceful failure of the connection. And again, we bail out. Okay. So we've almost finished now. We've created our connection, we've sent our request, we've got our response. The server's indicated that it's closed down. Now we need to close down ourselves. A connection close down can be initiated by either peer, either the client or the server. In this example, it's been initiated by the server. And the way that happens is a TLS protocol message is sent. A closed notify alert message in particular is sent. And that just indicates that the endpoint is shutting down in a graceful way. So either endpoint can send that, and then the other endpoint can reply with its own close notify. Once a close notify is sent by an endpoint, by either the client or the server, then no more application data can be sent from that endpoint. You can still receive if you haven't received a close notify yet, but you can't send anymore. In a lot of application protocols that have proper framing of the application data, by which I mean you know when you finished, you know how much data has been sent and that you finished sending data. In those kind of protocols, it's not uncommon for this shutdown phase to be omitted. So just be aware of that. But once the shutdown is complete, then we should free our SSL object as well. So let's just look at the code for this. So to do that graceful close down, we call SSL underscore shutdown, pass in the SSL object. In this particular example, We're expecting that to come back immediately with a successful result because we already know the server's closed down. We've just got to send our close notify, and that's it. We're done. If we get anything other than a positive result from that, then something else occurred. Bail out. Okay, and then the final cleanup steps here. We need to free some of these SSL objects that we've been creating. And we might also want to print any errors that might have occurred. So if we hit any of those blocks which said bail out here, then we might want to examine the OpenSSL error stack and see if we can get some further information about what happened. So we can call a function in the code there. It's underscore print underscore errors underscore FP. I'm passing in the standard error output. So this will just dump any errors that OpenSSL has in its error stack to the standard error output, which hopefully will give you some kind of clue as to what failed. And then we're going to free the resources that we allocated. So we call SSL underscore free. We pass in the SSL object that we created earlier. That frees up all resources with that SSL, and you can't use it again after that point. Optionally, if you're not going to create any more TLS connections, then you can also free the SSL context that we created. So you can do that with SSL context underscore free, pass in the context object, and that will free that as well. Obviously, if you are going to create more TLS connections, don't free that at this point, free that later. Okay, so we're almost done. I just want to spend, I've got a few slides on troubleshooting and dealing with issues that you might encounter. So you will remember that on the previous slide, I talked about this function print errors FP, which will dump out information on the OpenSSL error stack. A common error you might encounter is this one: certificate verify failed. So there could be a number of reasons for this. So for example, if you've not set up your trusted certificate store properly, then the verification is going to fail. Or maybe the server has sent us a certificate and we don't recognize the CA that has signed it. It's not in our trust store. Or maybe, if you remember, I talked about these certificate chains, the server certificate, the intermediate CA certificates. That whole chain needs to have been sent from the server, and if some of those certificates are missing in that chain, then that can cause this problem. Or maybe the host name that's in the certificate doesn't match the certificate verify host name that we set in our code earlier through the SSL set one host function call. If those don't match, the verification is going to fail. Or maybe the certificate's expired. So there's a whole slew of reasons that could be the cause of this. Check your configuration and make sure everything is as it should be. There are some callbacks that we can use to get more information from OpenSSL about what has happened. So one such callback is one we call the info callback. And this just enables you to get information about the state of a connection. Every time we run the TLS handshake, there are numerous protocol messages being exchanged, and each one represents a state change for the object, for the SSL object. And we can query what the current state is, and we could do that through the function SSL state string long. That just gives you a human readable string which tells you about the current state of the SSL object. So what you do is you create a callback, you set that callback through this function SSL CTX set info callback, and within that callback you query the state through SSL state string long, and you can put it in a log file or print it on the screen or whatever you want to do with it. Here's a sample info callback that you can use. I'm not going to go through this in detail. I'm just flashing it up on the screen here So if you do want to use this, feel free to take that code. It will be obviously this will be distributing the slides, and it will be on the YouTube video. So have a look at that if you want to use that. Another callback that you can use is one we call the message callback. And this provides detailed information about the protocol messages that are being sent and received by OpenSSL. We actually have a built-in implementation of the callback itself, which we call SSL trace. And what that callback does is prints all the information about those protocol messages in a human readable form. So you get detailed dumps of what the client's sending, what the server's sending back. You can see how far in the process it's got, and whether the communication is looking sane or not. And to do this, you first of all you need to create a BIO for, and that BIO is where to represent where the output from your tracing is going to go. So in this sample code, I call BIO new FP, and I pass in the standard out handle to create a BIO. And so that means that that BIO is just going to print all of this text to your screen. And then we use it through these function calls, SSL set message callback. We pass in the SSL object. We pass in the built-in callback SSL trace. And then we also call SSL set message callback arg, which again, we pass in the SSL object, and we pass in the BIO that we want to use. So if you just insert those 3 lines into your TLS client application before the handshake starts, before you've called SSL Connect, then you will get on the screen lots of detailed information about what's happening in the handshake. Okay, so finally then, here's some links to further reading and further information that you might find useful. If you want to find more information about TLS and certificates and trusted certificate stores, you can find that in our man pages. It's in the section 7 of our man pages. There's a link on the screen. Again, take a look at that once we distribute the slides. The code that I've presented here is all available. It's part of the OpenSSL distribution. So if you download the OpenSSL source code, if you look in there in the demos directory and then the guide subdirectory within that, there is a file TLS client block.c. It's got the full application that we've developed here in this webinar, and you can run that directly. There is also a whole guide which describes that code in detail, covering much of the same ground that we've covered today. That's also in section 7 of our man pages, and there's a link there. And then finally, there's also demos and a guide for doing the same thing, but extending what we've written today for using non-blocking sockets. So if you're interested in non-blocking sockets, that's the link there at the bottom. Okay.
Awesome.
That's everything.